Math, it's all about math, the wonderful world of math. Welcome to the wonderful world of math. Today on our episode, we want to talk about sequences. So here's our introduction to sequences. First of all, what is a sequence? A sequence is an ordered list. Usually it's going to be numbers, but it could also be shapes or other kinds of geometric figures. For example, I could use a sequence of numbers like 0, 2, 4, 6, 8, 10, and so on. Or I could use a sequence of shapes like square, pentagon, hexagon, and heptagon, and octagon. Or we could do one that's a figure that's not really a polygon here like these other guys. We could say something like, here's 3 dots. Here are more dots. Here are more dots. And we can build a pattern out of this. And we'll look at some of these more later, but these are examples of different kinds of sequences.
The next thing we want to do is talk about some of the notation and terminology we'll use for sequences. So if I have a sequence 3, 6, 9, 12, 15, etc., this has a number of what we call terms. The first term is 3, the second term is 6, the third term is 9, and so on. And we have a notation to denote the first term. We typically call the terms of a sequence A with different subscripts. So the first term is going to be A with the subscript 1, and the second term will be A with the subscript 2. So that each of these subscripts tell you which term you're talking about. This is handy because unlike using actual different letters for each term, A, B, C, D, etc., that list will run out at 26, which as far as infinite sequences go is pretty quickly. The nice thing about subscripts is that you just get bigger subscripts. You don't have to run out of letters, you just keep using A with a different numbered subscript, right? Now, here we've got a sequence, and in this sequence, the first term, called A sub 1, is 3. The second term in the sequence above is called A sub 2, and the second term is 6. The third term, A sub 3, is 9, and the fourth term, A sub 4, is 12. The fifth term, A sub 5, equals 15, and if you can guess, the sixth term, A sub 6, is equal to, that's right, you guessed it, 18, right? So we've got these symbols, these notations that describe a term in a sequence, in this case the fourth term. In general, the general term for the sequence is given by A sub n. And one of our jobs when investigating sequences is to try to find formulas for the nth term or the general term of a sequence. Now in this case, we'd like to ask ourselves, what do these all have in common? There are a couple of important types of sequences that we can use to help us predict patterns. But one of the first things that we ask ourselves is, what do these things have in common? Do they have anything in common? And if you notice, each of these numbers definitely has something in common. This is what we use to help predict that the sixth term would be 18. These are all multiples of 3. And so what does it mean to be a multiple of 3? It means that you can write that number as 3 times something. So 3 can be written as 3 times 1. And 6 can be written as 3 times 2, right? 3 times, 3 times, 3 times, 3 times. And you fill in those blanks. Go ahead if you didn't already. Okay, I waited for you. Here we go. And now we'd like to come up with a formula for the general term of the sequence. Now that we've identified what they have in common, and we were able to express them all as multiples of 3, instead of just realizing they were multiples of 3, we've expressed them as multiples of 3 by writing them as 3 times something. We look to see if this has any relation to the index, the subscript. So if this subscript, the index, is 1, then this is 3 times 1. If this index is 2, then this factor is 2. If this is 3, then, well, actually both factors are 3, but importantly, the second factor is 3. If the index is 4, then the second factor is 4. So it turns out that this second factor matches the index every time. So we know that any term in the sequence is going to be written as 3 times some number, and that number has to be the same as this index. So if the index is n, you're going to get 3 times the index n. This is the formula for the nth term, or the generic term, or the general term of the sequence. And this is really handy because it allows us to jump straight to any term you like. If you want the 100th term, you say a sub 100 is going to be 3 times, well, a sub 6 was 3 times 6, a sub 5 was 3 times 5, a sub 100 is going to be 3 times the index, 3 times 100. That is what this formula means. It means that I'm multiplying 3 by whatever number is down here as my subscript. So the 300th term would be a sub 300, and that's going to be 3 times 300. The 300th term is 900. Okay? Let's look at a different sequence. So here's our next example. I want you to look at this for a while, pause the video, and see if you can find a pattern. Tell me what the next 5 numbers should be. Alright, did you get it? Ready? Here we go. It's sort of easier to predict what the next numbers should be than to come up with a formula or to describe how to predict the numbers. Predicting them is easier than describing how to predict them, right? But that's what we want to do. We want to describe how to predict them. And so we want to look for what these things have in common. How do I get from one number to the next is one question we ask. And so this and the last one, actually, are both examples of a type of sequence, a family of sequences called arithmetic sequences, wherein each consecutive pair of terms has a common difference. So, for example, the first term taken away from the second term is going to be the same as the third term minus the second term, which is the same as the fourth term minus the third term, and the fifth term minus the fourth term. They're all the same. They all have the same difference. So that for any n, you take the nth term and you subtract the one just before it, you get the same number called d, the common difference. So for example here, we've got 5 and 4, and their difference is 4, and I said 5 and 4, 5 and 1, and the difference is 4. 9 and 5, and the difference is 4. 9 and 13, 13 minus 9 is 4. Every pair of consecutive numbers should have the same difference. Now if we take this example again, and because I said this was an arithmetic sequence, we should be able to find the differences between each pair of terms. 6 minus 3, 3. 9 minus 6, also 3. 12 minus 9, also 3. And 15 minus 12, also 3. Every one of these differences was 3. So we said that this was going to be 18, right? So that this difference, oh yeah, that's 3. If this is arithmetic, that means the difference between the next pair of terms is also 3. So what's 18 plus 3? That's going to tell you 21, and 21 minus 18 is 3, right? So this does fit that pattern. Cool. Alright, back to this guy for a second. Now, we said one of our big goals here was to be able to write this as the nth term, a formula for the nth term that tells us if we know really how to predict what's coming ahead, right? And we do go much further into this. on a future video in the series called Arithmetic Sequences. But let's just take this one example, well, this second example. Starting from the first term is a sub 1, right? Now we know that to get the second term, 5, we were able to say, here's 1, here's a number that's 4 units away, 5. So really what I can do is add 4 to 1, and then that will get me the next number, right? So what about a sub 3? A sub 3 is 9. That's our third term. Now we know that the difference between these two numbers is also 4. So I can say that 9 is 5 plus 4, but I also know that if I start from 1, I have to add 4 and then another 4 to get from 1 to 5 and 5 to 9. So this is really like taking 1 as their starting place and adding 2 4s. What about a sub 4? A sub 4, the fourth term, is 13. Now, to get from a sub 3 to a sub 4, we had to add 4, right? So you start from 9 and you add 4. But again, I can think about this as starting from the beginning, and I had to add 4, 4, and 4 again to get from 1 to 5 to 9 to 13. And that's going to be 3 4s, right? And so you end up just counting how many jumps it took you to get from the beginning to where you were. To get from 13 to 17 is just 4 units, but to get from 1 to 17, it took 4 and 4 more and 4 more and 4 more. It took 4 4s. Do we see a pattern building up here? If not, try writing a sub 6 this way. A sub 6, first of all, is 21. But I want you to try to write it like we have written each of these guys. So try it. And then if that's not enough, try a sub 7. I'll wait for it. Pause me and I'll wait. Okay, are you ready? Here we go. So this is what we get when we examine a sub 6 and a sub 7 and try to write them as 1 plus how many 4s. Now, if you compare each of these to the indices, you should start to see something interesting. And that's what we were interested in. It's going to help us determine the general term a sub n. A sub n, notice that the number of 4s is always exactly 1 less than the index. Index 7, we had to add 4 6s. So if I have a starting place of 1, I have to add 1 less 4. So that's 4 times 1 less than the index. There's 4 times 1 less than the index. If your index is 100, the 100th term is going to be 4 plus 100 minus 1, or 99. So that's going to be 1 plus 396, or 397. So here's another type of question I might ask you for something like this. Is 100 a term in this sequence? If you have discovered the nth term formula, then this is as simple as setting up an equation and solving it. You may have noticed that for all of these terms, the index, the subscript, is only allowed to be natural numbers. So if 100 is a term in the sequence, that means that I can say a sub n is 100. And a sub n in this sequence has the formula 1 plus 4 times n minus 1. If 100 is a term in the sequence, then this equation will have a natural number for a solution. So let's solve it and find out. To get n on one side by itself, we should subtract 1 from both sides. 99 equals 4 times n minus 1. And now we can divide both sides by 4, and you get 99 divided by 4 equals n minus 1. And when I add 1 to both sides, 99 fourths plus 1 equals n. And even when you get a common denominator and add, you should see that n is not going to be a natural number. N is going to be 103/4. 103 is not divisible by 4, so n is not a natural number. N is not in the set of natural numbers. Which means that there is no index I can give A that would make this formula equal to 100. So 100 is not a term in this sequence. Here's an example of a new type of sequence. The first term is 2, the second term is 4, the third term is 8, and 16, and 32, etc. Can you tell me the next two terms of the sequence? Are you ready? If you said 64 and 128, you guessed correctly. So what's special about this sequence? Is it an arithmetic sequence? If you look at the difference between terms, this is 2. If you look at the difference between these two terms, it's 4. The difference between these terms is super not the same. But there is something that is predictable. If you think about this as how to get from here to here, and how to get from here to here, and how to get from here to here, etc., then the pattern might be a little bit easier to detect. What we're doing to get from one term to the next is multiplying by the same thing each time, rather than, with the arithmetic sequence, adding the same thing every time. Each time you added 4 to get from one term to the next. In this sequence, you are going to be multiplying by the same thing each time. So that if I take the difference, I don't get anything really revealing, but I do get something really helpful if I take the quotient, the ratio of consecutive terms. 4 divided by 2, and 8 divided by 4, and 16 divided by 8, and 32 divided by 16, etc. They're all going to give you the same thing. It's that same number that I said I can multiply by to get the next term. I can start here and multiply by 2 to get the next term, and this ratio of one term to the previous term is 2. This is an example of geometric sequences, a sequence where every pair of consecutive terms has a common ratio. Instead of a common difference like arithmetic sequences, these have a common ratio. And in general, that means that if I take the second term and I divide it by the first term, I get the same thing as when I take the third term divided by the second, or the fourth term divided by the third, or the fifth term divided by the fourth, and so on. And in general, for any n, if I take the nth term divided by the one before it, I get the same number called r for a ratio, the common ratio, that all of these quotients are the same. For more information about geometric sequences, you can see the later on edition of this video series called Geometric Sequences. We go into more detail and do a bunch of examples with that kind of stuff. Let's focus on finding the nth term for this sequence. One of the things we saw that's helped so far is to try to write the various terms in different ways using what we know about them. So here we are taking the notations with their subscripts, their index, and these things. Now, the other thing we know about these is we know that each term divided by the one before it is the same every time, but we also describe that not just as division, but as multiplication, to get from here to here, that I can multiply by the same thing as getting from here to here. So that the second term is also going to be the first term times 2, right? To get from here to here, I can multiply by 2. To get from here to here, I can multiply by 2. So that says the third term, 8, is equal to the previous term times 2. And a sub 4, the fourth term, is going to be the previous term times 2, right? Only, what if I want to go to the 100th term? This is obviously less great of an idea than for arithmetic sequences, where we could actually sort of calculate that sort of thing. But let's think about this anyway. To get from here to here, I multiplied by 2. To get from here to here, I multiplied by 2. So to get from 2 to 8, I multiplied by 2, and then 2 again. So this is going to say 2 times 2 times 2, or 2 times 2 times 2 if you're not into the whole parentheses thing. Now a sub 4. To get from here to here, 2. Here to here, another 2. Here to here, a third 2. Right? So we start with 2. And in order to get to 16, I have to multiply by 3 more 2's. A sub 5. A sub 5 is 32. This is the previous term times 2. Or, starting from the beginning, that's 1, 2, 3, 4 more 2's. Starting from 2 and multiplying by 1, 2, 3, 4 more 2's. So, now we should have an idea of the pattern, right? A sub 1 equals 2. A sub 2 equals 2 2's multiplied together. A sub 3 equals 3 2's multiplied together. A sub 4 is 4 2's all multiplied together. A sub 2 is better written as 2 squared. We have notation that is designed for this express purpose of writing repeated multiplication of a number with itself. So that a sub 6 is going to be 2 to the 6, that is 64. And in general, a sub n is going to be the nth power of 2. Every geometric sequence should have something raised to a power. So here's our next example. If you try to find the differences between each pair of terms, you're going to find pretty quickly that this is not an arithmetic sequence. The difference between the first two terms, 5/6, and the difference between the next pair of terms is 1/2. Those are not the same. If you try to find the ratios of consecutive pairs of terms, a sub 2 divided by a sub 1 turns out to be 3/2, and a sub 3 divided by a sub 2 is 6/5. That's not the same at all. So it's neither arithmetic nor geometric, but we should be able to predict the pattern. Now, one of the tricky things about this is that given this sequence the way it is going to be harder to predict the pattern. But if I write these in just the right way, using not these versions, but equivalent fractions, you can see, for one thing, why it's helpful to not reduce when looking for a pattern, or maybe to reduce them the right way. If I'm given this equivalent sequence, the pattern becomes much easier to see. You'll notice that 10/4 is the same as 5/2, and 15 divided by 5 is the same as 3, and so on. But this sequence makes it easier to see the pattern. Now, if I'm asking you to come up with the nth term, and you've got something like fractions, maybe you don't want to try to find a formula for the numerator and denominator together as a single fraction, but maybe you want to examine what's happening up top on its own. Describe what's happening in the numerator. What do all those numerators have in common? Now, that should be a pretty easy question, right? They're all multiples of 5. So the numerators are all going to be 5 times something. In this case, 5 times 1, 5 times 2, 5 times 3, and so on. And then we say what's happening in the denominator. The denominator starts at 3. The next one is 4. What can you tell me about this denominator? 3, 4, 5, 6, 7, 8. They're all going up by 1 each time. So that is something we can predict. It starts at 3 and it goes up by 1 each time. So if this is 3, this is 4, this is 5, this is 6. Do we see a relationship between this number and this number, this number and this number? the index into the denominator, the index into the denominator. Yeah, we do. We should see that this number, the denominator, is bigger than this by 2 units. That's right, we set it 2 units. So what we should get is that the numerator is going to be 5 times this number, and the second factor match. Index, second factor, match, 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 match. 5 times the index. And the denominator, we know that the denominator was always going to be 2 bigger than the index. So if the index is n, you say n, and 2 bigger than that is n plus 2. So if you deal with the numerators and denominator separately, you can find patterns for the numerator and find patterns for the denominator, and just make a fraction out of it. It turns out that the numerator and denominator are both arithmetic sequences. The sequence a sub n as a whole is not arithmetic at all. But the numerators of our sequence are an arithmetic sequence, and the denominators are a different arithmetic sequence. So that's interesting. So make sure that you're thinking about stuff like that you don't have to do every part of the sequence, and that also if I give you something like this, maybe you don't want to reduce these fractions. Normally, in the normal course of events, you would and should. But to find patterns like this, it was helpful to not reduce these fractions. Let's try something a little different. This time I'm going to give us the formula for the nth term of a sequence, and I'm going to ask us to use it to come up with a number of terms. So we'll start by saying, what are the first 5 terms of the sequence? The first 5 terms of the sequence are the terms that have subscripts 1, 2, 3, 4, and 5. So that means that we're looking for a sub 1. That means that I'm going to take this formula that I was given and plug in the first 5 numbers for n. So a sub 1, the first term, is going to say 1 squared minus 3 times 1 plus 5. And you simplify. 1 minus 3 plus 5. That's 1 plus 5, 6, minus 3 is 3. The second term, a sub 2. This is exactly what the notation a sub 2 means. It's the second term. A sub 2 is what I get when I plug in 2 for n. So we get 2 squared minus 3 times 2 plus 5. And of course, you get some simplifying. That's 9 minus 6 is also 3. Okay, so I want you to pause this and try to find the next 3 terms. Okay, did you get it all? Here we go. The next terms of the sequence should be 5, 9, and 15, and here's the work. Now let's look about, is this an arithmetic sequence? Do the terms have a common difference? The differences of the terms, 0, 2, 4, already these differences are different, so you can tell it's not arithmetic. But if you look at the differences anyway, you see that there is a pattern. 2, 4, 6, you should notice that all of the differences are going up by the same number. So the difference of the differences is the key to the sequence. You look at the difference of the differences, and it ends up being the same every time. So that we predict that the next difference of terms is going to be 8, right? Because 6 plus 2 is 8. And so then you do that again, and the difference of differences would be 10. So if these two terms had a difference of 8, then the next term would be 15 plus 8 is 23. And then the difference of the next terms would be 10, so this next term has to be 23 plus 10, 33. And so this is not an arithmetic sequence, but I can predict the next terms. And they also, of course, do fit the formula that we came up with earlier. Well, that's about as much as we can fit into one video, so join us next week, same bat time, same bat channel, for the next video in the series on recursive sequences, figurate sequences, totally forgot. Okay. So, in the meantime, the word of the constellation of the day, it's not one word, it's 2 words, it's Canis Venatici, and this has been a Badger Bear production. Bye for now.